Alright, in this video we're going to talk about solutions and molarity. So solutions are homogeneous mixtures of two or more substances. And we talked about homogeneous mixtures back in the first chapter. And so another name or synonym for homogeneous mixture is solution. And as we talked about in that chapter, when we have solutions, the components of the mixture are mixing at the atomic and molecular level. And one of the things that characterizes solutions is that there are no visible boundaries between the components. When we talk about solutions, there are two components, typically. There's the solvent, and that's the substance present in the greater amount, and then there's the solute, which is the substance present in the lesser amount. And so the way we talk about solutions is we say the solute dissolves in the solvent. And typically, because the solvent is the major component, there's typically only one solvent, but we might have multiple solutes dissolved in that solvent. Now, a lot of the solutions that we'll talk about involve having a solid solute and a liquid solvent, and that liquid is very often water, but it doesn't have to be. Any homogeneous mixture can be thought of as a solution, and so there are lots of different examples, right? So sugar dissolved in water, sugar is the solute, water is the solvent. Alcoholic beverages are solutions where both components or both major components are liquids, right? Alcoholic beverages are mostly water, but they have some ethanol in them, and so in this case the ethanol is the solute and water is the solvent. The air that we breathe is an example of a solution. Oxygen and other gases are the solutes, and we can think of the major component, nitrogen, as being the solvent. Alloys, which are mixtures of metals, are also examples of solutions. And so bronze is basically the element tin dissolved in the major component, so the solvent, if you will, copper. So another bit of vocabulary, solvation is the process where the solute particles are surrounded by the solvent particles, and we could also call this dissolution. So when the sugar dissolves in the water, right, we start with a solid crystalline sugar, and then the water molecules come and surround the solute. And this, if we're having sugar, then these would be the glucose molecules. And so this process of solvation occurs when the solute molecules are surrounded by the solvent molecules. Now, water is going to be one of the most common solvents that you use as a chemist. And so we have a special name for solutions in which water is the solvent, and they're called aqueous solutions. And when we're doing chemical equations, we'll abbreviate substances that are dissolved in water with the symbol AQ, meaning they're aqueous. And so, just more vocabulary really, when we talk about hydration, this is solvation, but it's the term specifically used when the solvent is water. And so one important thing about water is it's a covalent compound, and so we know that in covalent compounds, the elements that are connected by those covalent bonds share their electrons. But in the case of water and many other covalent compounds, the sharing isn't 100% equal. And we'll talk about this a lot more in 1212, but it turns out the oxygen gets the electrons that are shared more than the hydrogen does. They spend more time close to the oxygen than they do to the hydrogen. And so the result of that, because electrons are negative, and if the oxygen gets the electrons more of the time than the hydrogen, that means that a slight negative charge builds up around the oxygen end of the atom, and slight partial charges end up near the hydrogen atoms. And so it's not an ion, it's not full-on charges, and so we use the Greek letter, lowercase letter delta, to represent that they're partial charges. So oxygen's not a full-on negative, but it has a partial negative charge, and hydrogen has a partially positive charge. And so we might indicate that here like this. The oxygen end of the molecule is slightly negative, the hydrogen end is slightly positive. And so particularly when ionic compounds are involved, what allows them to mix with the water is the fact that we have this separation of charge. And when we have this unequal sharing of electrons and we have a buildup of negative charge on one side and positive charge on the other, we say that that molecule is polar. And so water is an example of a polar molecule, and it's this polarity that is largely responsible for water being such an effective solvent, particularly for ionic compounds. Now, one important thing that happens with ionic compounds, because we know we don't have molecules, we just have individual ions. And so during the hydration process, during the solvation process, what gets hydrated is the individual ions. And so when something, if we imagine this being sodium chloride, where the sodium is positive and the chlorine is negative, I don't have NaCl's floating around in the solution. I have individual chlorine ions and individual sodium ions floating around separately. And if you notice, the hydrogen end of the water is the positive end, and so that's the end that's attracted to the negative chlorine ions, and the negative oxygen end of the water molecules is the end that's attracted to the positive sodium ions. And so the fact that we separate the ions from one another when ionic compounds dissolve in water, the solute is said to dissociate or ionize upon dissolution. And so we really have individual ions floating around. We don't have NaCl molecules floating around because there is no such thing as an NaCl molecule. We have the individual ions that are hydrated by the water molecules. Now, many ionic compounds dissolve in water, but certainly many covalent compounds do as well. And most of the covalent compounds that are soluble in water, that can be dissolved in water, are also polar, right? So they have these partial negative and partial positive charges. So ethanol is a covalent compound that is very soluble in water. It's very easy to dissolve ethanol in water because it has these OH covalent bonds where, again, we have a partial negative charge built up on the oxygen, a partial positive built up on the hydrogen. And so then the negative oxygen end of the water molecules are attracted to the positive hydrogen in the ethanol. Now, covalent compounds do not dissociate when they dissolve. So they're still solvated, they still get surrounded by the water molecules, but they don't break apart. The covalent compounds remain intact. Now, something that we'll talk about in the next chapter, one exception to that is acids. And so acids are covalent compounds that do dissociate, but we'll talk about that more later. Now, because solutions are mixtures, they aren't fixed composition. So I can have more or less of the solute dissolved in the solvent. And so we need some way to quantify that. And as we'll see, there are many ways to do that. One of the most common ones that chemists use is called the molarity. And the molarity is defined as the ratio of moles of solute divided by the total volume of the solution. And so to write that as an equation, the symbol that we use to represent molarity is capital M. And be sure you capitalize it. Lowercase m we usually use for mass, and so when you're talking about molarity, be sure you use capital M. And as we'll see, there's another unit of concentration that's represented by lowercase m. So capitalization in chemistry is generally important. And then so the molarity is equal to the moles of solute. And so one symbol that we often use in chemistry to represent the amount of moles is the lowercase n. So the molarity is the moles of the solute divided by the volume of the solution. And as far as units go, the moles of solute has to be in the units moles. The volume of the solution has to be in liters. And so then the units of molarity, like if you're expressing a concentration of molarity, you can either use capital M or you can use moles per liter. So M, writing capital M, is equivalent in terms of units as saying moles divided by liters. Alright, so I have one example here, and then I have another video with additional examples of the types of problems we can use involving molarity. In this case, we want to know how many grams of solute there are in a 725 milliliters of a 0.460 molar solution of sodium nitrate. And then they've helped us out a little bit. We don't have to calculate the molar mass of sodium nitrate because they gave it to us. Alright, so we may be a little bit confused at first because they're talking about the grams, and there's no grams in my molarity formula, right? Our molarity is the concentration, or the molarity is the moles of solute divided by the volume of the solution. And so while there isn't grams in this formula, in previous videos we have seen how we can convert from moles into grams. So they gave us the volume, they gave us the molarity, so we should be able to calculate the moles of the solute, in this case the sodium nitrate, and once we have the moles, I can then use the molar mass of sodium nitrate to find the grams. All right, so this is one of the instances where I like to rearrange my variables first, right? So I'm solving for moles, so I need to get the moles by itself. So I'm going to multiply both sides by the volume, and so N is equal to M times V. And so now I can go ahead and plug in my numbers, but I have to be careful. I have the molarity as 0.460, but the volume has to be in liters, and they gave me the volume in milliliters, right? And so I know that 1 milliliter is 10 to the minus 3 liters. So if I take my 725 milliliters, I have 0.725 liters. So I can see how my units cancel. Rather than writing capital M for molarity, I'm going to instead write moles over liters, because now I can see when I multiply by that volume in liters, right, I have a liter on the denominator, a liter in the numerator, and so those will cancel. And so the number of moles of my solute in this case, 0.334 moles. And so that's my moles of solute. To convert from moles to mass, I need to multiply the moles by the molar mass. They gave me the molar mass, so I'll take my 0.334 moles times 85 grams per mole. So my moles cancel, and 28.3 grams of sodium nitrate, NaNO3.